So we're continuing right along here with the G proof, our rigorous mathematical proof that God exists using first-order predicate logic and 5 axioms that no scientist can reasonably deny. This is video 5 out of our 9 videos, and this is a crash course in predicate logic, part B, about uniqueness. We have a website at thegproof.org. I'm Mark Lawrence Donald Emerson, and I'm your teacher. So here's a map of all the videos, and you can see we're getting a lot of cyan color on here now. We've got 4 of them done. And so just to recap, in video 1 we did our introduction and overview, and in these 4 videos on the left here, I'm teaching you the logic, the mathematics that you need to know to understand our proof that God exists. So in video 2 we did geometry proofs, and in video 3 we did a sentential logic. And then in video 4 we did the first half of predicate logic about quantifiers. Now we're using, this is accumulating. And now in video 5, which is this video, we're going to do the second half of predicate logic, part B, which is about uniqueness. And then after all that, then we're going to move over here to the right-hand side, and we're in videos 6, 7, and 8, I'm going to teach you about the proof. In video 6, we'll do our undefined terms, definitions, and the first 3 axioms. And then in video 7, we'll do the last 2 axioms. We'll show that the axioms are consistent, and we'll do an informal proof that God exists, which doesn't count. And then in video 8, we'll do the proof that counts, the formal, rigorous proof of the G theorem that God exists. And finally, in video 9, we'll talk about the consequences of the proof. Okay, so here we are in video 5, and so let's move forward here. Here's our outline of this video. We're going to talk about, we're going to give you a quick summary of the rules that we've done so far in videos 3 and 4. Then we're going to talk about how to express uniqueness. Now we have 3 different formulas for expressing uniqueness. We have the long uniqueness formula, LUF or LUF. We have the medium uniqueness formula, MUF or MUF. And we have the short uniqueness formula, SUF or SUF, which is the upside down E with the exclamation point added. Then we're going to prove that the LUF and the MUF are equivalent to each other. We're going to do that in this part of the video. Then we're going to go on and show that the MUF and the SUF, we're going to show how to get back and forth between them using 2 new rules. And then finally I'm going to talk about descriptions, which is the logical symbol that means the, or the, which is the candy cane. Okay, so let's look at a summary of rules 1 to 14. Here we are in our outline. And I'm just going to put this up as one page. We've talked about this before. We have proof starting rules and inference rules and proof ending rules. So we have one proof starting rule, which is our claim rule, which we use to begin a proof. Also ACP, which I'm counting, when I'm putting numbers on, I'm counting it down here with CP. That's for starting a conditional proof. We have 10 inference rules. Now we learned the ones that are in dark blue are the ones we learned in video 3. So modus ponens, repetition, simplification, adjunction, BC, and CB. And then we added to that in video 4 UI, EI, EG for quantifiers, and then SE, substitution of equals. And we have now 3 proof ending rules, which enables us to write done and then box and cancel. We have CP, that's conditional proof, and DP, direct proof, from sentential logic, video 3. And then in video 4 we added UP, which is universal proof. Okay, so now how do we express uniqueness? Here we are in our outline. Let's a little review here from video 1. I talked about uniqueness in video 1. So I'll just go back over this here. Uniqueness means one of a kind. So let's consider 3 qualities about operas. Operas by Mozart, operas by Beethoven, and operas by Brahms. So Mozart wrote 22 operas. Beethoven wrote 1 opera, and Brahms didn't write any operas. So there are 3 possibilities for equality. They're either 2 or more things have the quality, or exactly 1 thing has the quality, or nothing has the quality. So now, uniqueness happens in the middle case, when there's exactly 1. So an opera by Beethoven is unique, it's Fidelio. And uniqueness fails in the other 2 cases. An opera by Mozart is not unique. It could be Don Giovanni, Così fan tutte, Marriage of Figaro. He wrote 22 of them. It's not unique. In one sense, because there are too many. And in Brahms, an opera by Brahms is also not unique because he didn't write any. It's not unique the other way. Okay, so now, when we express uniqueness, we can say exactly 1 by saying 2 things. We say at least 1 and at most 1. Okay, if we say at least 1, that eliminates the nothing case. If we say at most one, that eliminates the two or more case. So, at least one and at most one forces the middle case where uniqueness happens. So to say Beethoven wrote exactly one opera, we can say two things. Number one, Beethoven wrote at least one opera, and Beethoven wrote at most one opera. And now, how can we use predicate logic to say this? That's what we're going to do now. We're going to say at least one and at most one using predicate logic. So, and we're going to do that with the long uniqueness formula, LUF. Okay? So, long uniqueness formula. Let's use this predicate right here, F. Let's say F, the predicate F means blank, is an opera by Beethoven. Okay? So, the LUF is going to say at least one and at most one. So now what we do first is we say Beethoven wrote at least one opera. If he wrote at least one, it means that an opera exists by Beethoven. And this right here says, there exists a T such that FT. In other words, there exists something T such that T is an opera by Beethoven. This says there exists an opera by Beethoven. In other words, Beethoven wrote at least one opera. Okay? Then second, we say Beethoven wrote at most one opera. Now, how do we do that? What this means is if any two operas are by Beethoven, then they're equal. This is an opera by Beethoven, this is an opera by Beethoven. If that's true, then we know these are equal to each other. That's the same thing, because he did not, it's at most one. So if two things claim to be an opera by Beethoven, they're both Fidelio. Now, how do we write that in predicate logic? Look at how this is. We have two universal quantifiers. Say, for all W and for all X, if, now see on the left side, we've got a conditional. On the left side of the conditional, in parentheses, we have a conjunction. FW and FX. In other words, W is an opera by Beethoven and X is an opera by Beethoven. See that? Okay, if W and X are both operas by Beethoven, then what happens? W equals X. You see that? So for any two things, for all W, for all X, okay, take any W you want, and now once you got a W, take any X you want. If W and X are both operas by Beethoven, F, W, and FX, then W equals X. This says Beethoven wrote at most one opera. But very important, it doesn't say he wrote at least one, because if he wrote none, this works for Brahms. If I were to say this is an opera by Brahms, this would still work. If any two things are operas by Brahms, they're equal. Well, the thing is, you will never find any two things. You will not even find one thing. It still works. It still comes out true. This says at most one, but it doesn't say at least one. This up here says at least one, but it doesn't say at most one. What we need to do now is put these two together. So we're going to put them together with and to say Beethoven wrote exactly one opera. Now look at this formula here. Look carefully here. The outermost statement here is a conjunction. It's this and right here. And on the left of that and is this formula right here, this statement. And on the right-hand side of that and is this statement. So on the left we say there exists something T such that T is an opera by Beethoven. In other words, Beethoven wrote at least one opera. And if there are any two things, X, W and X, such that both of them are operas by Beethoven, then W and X are equal. In other words, Beethoven wrote at most one opera. Okay? So he wrote at least one, and he wrote at most one. That means he wrote exactly one. This is the long uniqueness formula. See? It's the LUF. It's in this form exactly right. The big advantage of the LUF, the long formula, is that once you capture and understand what I just said, you can see. You can look at it and say, oh, I see. There's a conjunction there. On the left side of the conjunction said there exists something that F's. And on the right side, it says if there are any two things that both F, then they're equal to each other. This means that F is unique. Okay. So the advantage of this formula is you can see by looking at it and understanding the predicate logic, oh yeah, it does. It says exactly one. So now let's talk about the medium uniqueness formula? Well, once again, we're going to use F as an opera by Beethoven. The MUF, the medium formula, is a shorter way to say exactly one. It uses using the quantifiers we already have. Here it is. Now this is a little weird. You see, it's shorter than the long formula. It says, there exists something Y, such that for all Z, Z is an opera by Beethoven if and only if Z equals Y. Now that's a little bit confusing. It's not so easy to see that says Beethoven wrote exactly one opera. But it does. It says it, like I said, but it's hard to see. Now, I don't expect you to believe me. I don't expect you to believe, oh, I just said that. That means exactly one. Well, the long formula, I expect you to be able to see it because you can see the pieces, how it fits together. This one isn't obvious. And so what we're going to do is we're going to prove that this one is equivalent to the other one. And we're going to do that in examples 6 and 7. And then once we know, by the proof we're going to do in this video, that the medium formula says exactly one, then we're going to use it later in the G proof. See, the thing about the medium formula is since it's shorter and it's easier to use in a proof. And so the long formula is so long, it's cumbersome to use in a proof. We want to use this one because of the efficiency we gain by it. But we have to prove it's equivalent. We have to prove that this really does mean exactly one. All right? So now, let's talk about the short uniqueness formula. Well, once again, F means an opera by Beethoven. And here it is, right here. This said, now what this does, this is a new quantifier. It says a backwards E with the exclamation point, okay? And what this says Beethoven wrote exactly one opera. It does it when I say it's a new symbol. I mean the backwards E and the exclamation point go together. So this is called the uniqueness quantifier. The backwards E with the exclamation point. It's a quantifier. What quantity? Exactly one. The exclamation point matters. You can imagine the exclamation point and the backwards E are glued together as one symbol. All right. Just like if you have a lowercase I, you have a dot. The dot and the bottom part of the I, it's one symbol. You don't think of the symbol, the dot and the bottom part of the I as separate. Okay, this actually has three. The exclamation point has a dot too. They go together and now it's glued with the E, the backwards E. All right. So now, the SUF, that's this thing here, it's an abbreviation for the MUF. This formula is an abbreviation for our medium formula. Okay? So this says there is exactly one, if we write this statement here, which is the same as up here, okay? This says there exists exactly one thing X, such that X is an opera by Beethoven, because that's what the blank is. Okay? There exists exactly one thing X, such that X is an opera by Beethoven. That's what it says. In other words, exactly one opera by Beethoven exists, or Beethoven wrote exactly one opera. Now, I don't expect you to see why it says that yet. Well, it's an abbreviation for the medium formula. And the rest of this video, or most of the rest of this video, I'm going to explain how all this fits together. Okay, in fact, here they all are. The long one, the medium one, and the short one. So the long one, just recapping here, this long formula here, it's easy to see. You can see the at least one and at most one. Okay? The medium one is useful in proofs because it has the regular quantifiers, which we can use UI and EI and those rules on these quantifiers in a proof. And then we're going to prove, like I said, that it's equivalent to this one. The short one is compact and focused, and once you know the lingo and once you have the rule to get back and forth between these two, then when you write that, oh, I see, it's just saying it right there. Whatever F means is unique. Okay? All right, so now we have to prove the equivalence of the long and the medium formulas, luff and muff. All right, so here we are in the outline. And so what we're going to do is we're going to prove that the luff, if and only if, the muff. We must prove they are equivalent. And remember, equivalent means you get the biconditional, if and only if. So here's a long one, here's a medium one. We're going to prove that the long one, if and only if the medium one, and this is it. Look at this long thing here. This is what we're going to prove in just a moment. Now let's look at this formula here. What is the outermost statement here? The outermost statement is this biconditional right here. Now what's over on the left side of that biconditional? All of that on the left of that biconditional is the long formula up here. See that? I've copied that exactly to the left side of this biconditional. And on the right side of that biconditional is this formula right here. We're going to prove this big, hairy, long thing. Now, it's a biconditional, right? So to prove a biconditional, how do we do it? We prove the forward conditional, and then we prove the reverse conditional, and then we use CB to put them together in a direct proof. The problem I'm having here is that the proof is too long to fit on the screen. So what we're going to do is I'm going to break this down into two examples. In example 6, we're going to prove the forward conditional. And then, in example 7, we're going to prove the reverse conditional. And then I'm going to in your mind, you can say, okay, well now if those are both proven, we can put them together with CB and it's done. Okay? So here we are in our outline. Now we're ready to do example proof 6 to prove that the long formula implies the medium formula. So here's the proof up here. Okay, proof number 6, the long uniqueness formula implies the short uniqueness formula, the medium one. This is the forward direction. Here's what we're trying to prove. Now what I've written in to prove here is that very same thing I just wrote on the other side. You can see, except that, what I've done is I've changed that biconditional in the middle, right here, is now a conditional. All right? This is showing the medium one is over here on the left, implies, the long one over here on the left implies the medium one on the right. And we're going to start with, we're going to have 4 columns. And in the what we're going to do is we're going to begin with the claim rule. And you know what? This statement is too long to fit here. So I'm just going to, as I go, I'm just going to refer to it up here. And so that's by the claim rule. And so, all right, now, what have we got here? We're trying to prove. Now remember, every time I need to refer to line 1, we just look up here. I'll make this yellow just to remind us. Okay? So we're trying to prove this thing, and what is the form of it? It's a great, big, hairy conditional. Okay? So we have this pink thing, this big, long, hairy, yellow, pink thing, implies this not quite as long blue thing. Okay? So we use conditional proof, and we'll assume the pink by ACP. And now, since these, what we're dealing with, we're dealing with some longer statements, hairier statements in this proof. You've got to watch a little bit carefully. So you've got to look carefully, see that, copy that down right. Does this pink really match this one here? If you need to stop the video to check that, go ahead. I can't go too slowly because I only have so much time. But this pink here does indeed match that pink there. Okay, and we're going to try to get the blue. All right, now what have we got here? This statement here is actually a conjunction. It's this pink part and this long blue part. And so I'm going to use my rule of simplification from sentential logic and pick it apart. And I'm going to take, so if I have pink and blue, then I can get pink, or I can get blue. Well, I'm going to take the pink like this, which is that one there, and that's from line 2 by simplification, okay? Now what does this say here? Exists a t such that ft. Well, I'm going to use my rule existential instantiation. If I know there exists something that f's, then I can say some particular thing. I get to pick some variable to put in there. Okay, so I have here, in this statement, I have the exists a t and then a pink thing in there. The blue variable is, that's the variable of quantification. This is the t, the blue one. And I have the blue one in there. That's just like this here in my rule. So now I get to copy down the pink and put some new variable. It has to be a brand new variable. I'm going to pick A. So I'm going to get FA by this rule here. This is from 3 by EI. Okay? All right, now what? Well, coming back up here to line 2, which is a conjunction, pink and blue. Now I'm going to use simplification the other way, and I'm going to take the blue, this big long one. Okay, and that's from line 2 by simplification. Now look carefully, make sure that the blue here and the blue here are the same. They are. Okay, now what? Well, look at, we're gonna make another claim. Here's what I'm going to claim. I'm going to try to prove this thing. We'll see in a minute why. That's by the claim rule. Now, look here. If we line 1, remember, is up there because I don't have room for it. If we look at the right-hand side, what we're trying to prove in the outermost proof here, we're trying to prove a conditional. And the right-hand side of that conditional I have mostly made yellow, but not all. I have not included the exists a y on the outside. Okay? So what I have here is the same as that, except that the exists a y is missing. The other thing that's changed is that what's a y here is an a down here. Now, why am I doing that? Well, that'll become clear as we move forward. Anyway, this is what I'm going to try to prove. All right, now what? In order to prove this, I have to use, it's a universal statement. I got to use universal proof to prove a universal statement. And I have to, so what I'm trying to prove is I'm trying to prove for all z, and then this pink statement inside. It's still a little bit of a long statement. It's got a whole biconditional in there. Fz, if and only if z equals a. All right? Now, in order to do the universal proof, I have to make sure that the blue variable is not free anywhere up above. And that variable is z. Do I have any z's up here? As a matter of fact, I do. I have some z's right up here. They're in line 1, even though they're sitting up here. Now, are they free or are they bound? Well, this first one here, this is bound. This says for all z there, and that is capturing the z by the f. It's also capturing the z in by the equal sign there. So both of these z's up here are bound. Yeah, they're bound. They're not free. Are there any other z's anywhere? I don't see any. So that means we're good to go on this universal proof. So what we have to do now is we have to try to prove this pink statement inside with these blue variables free. All right? That's where we're trying, that's our goal in our universal proof. Okay? So, now, let's move forward. What are we going to do? How are we going to prove that? Well, I'll tell you what. We're going to put another claim. And what we're going to claim, this thing here, by the claim rule, is, you see, what I'm trying to prove, and what I'm trying to prove in the parentheses up there in line 6, is I'm trying to prove a biconditional. And to prove a biconditional, which is I made that biconditional pink there, I have to do the forward proof and the reverse proof and then use CB. Well, what I've got here in line 7, I've written the yellow statement from line 6, but I've changed the biconditional to a forward conditional. See that? All right. So this, now I'm here at this proof. Now I'm at my third level. I'm at my third level of indentation. Now I need to go in again from here as I move forward. What kind of proof is this? This is, it's a conditional, isn't it? I'm trying to prove if pink, then blue. So I'm going to assume the pink. And see, I haven't said anything yet, but as you know, as I've been saying before, that we have to keep indenting as we go. And by the way, let me just say it right now, and I'll say it again when I think of it. If you're not following some of the stuff based on stuff I've taught you before, please go back and review video 3 and video 4 as needed to learn these principles. Or if I'm going a little too fast, stop the video, back up. Okay? I'm going a little faster now because I'm expecting you to know what I've taught you in videos 3 and 4. All right. So this is by ACP, and so we have to try to get the blue now in this conditional proof. All right, now what? Well, let's look at line 5 here. Line 5 is, on the outermost statement, is a universal statement for all W, it says. All right? So I'm going to use UI on that. Since it's a universal statement, then I can put anything I want in for W. So here it is, just like this in the rule. I've got for all W, and then I got this big pink thing inside here, which has a couple of W's in it, which are the blue dots. The blue dots are on the W's, okay? All right, so that means I can put anything I want in for the W to be my red variable, and I'm going to pick A. Nope. I'm going to pick Z. I called that wrong. Okay, I'm going to put Z in where the W's are. Okay, so I've copied the pink part of this statement down here, and I've changed the W's into Z's. And that came from line 5 by UR. Okay? All right, now what? Well, look at this statement here. This is another universal statement. This time it says for all x. I'm going to use UI again. I know for all x, this thing inside, okay, so x is now my blue variable, and the thing inside there is the pink part, and so I've got a couple of x's in there, both blue. I can put anything I want in for x, and this time I'm going to do the a. I had it backwards before. So I'm putting a in for x, right there. You see? So I've stripped off the for all x, and now I have the pink part alone, but I've changed the x's into a's, okay? And that comes from line 9 by UI, all right? Because I know that everything does it, so that means A does it, whatever this pink statement is. All right, now what? We'll look at lines 4 and 8. Blue, pink. I can use this rule adjunction. If I know the pink thing and I know the blue thing, then I can say pink and blue, right? Okay, so that's what I'm going to say. I'm going to say pink and blue. I've got the pink one here, FC. I've got the blue one there, FA, which means I can say FZ and FA, right? And where does that come from? From 4 and 8 by adjunction, okay? Sentential logic. All right, now what? Well, look at this. In line 10, I have pink implies blue. That's a conditional. And in line 11, I have the pink. I have the left side of this conditional here, see? F, Z, and A. That's what's on the left side of the conditional in line 10. And in line 11, there it is. That means I can use modus ponens and get the blue on the right, see? I get Z equals A. And where does that come from? Lines 10 and 11 by modus ponens. Okay? Well, look at this. We're at our third level proof in here. We got this outermost proof, and then we got a middle one here that starts in line 6. The outermost one starts in line 1. The middle one starts in line 6. The inner one starts in line 7. And I have just reached my goal. That one in line 7 is a conditional, right? I'm trying to prove pink implies blue in line 7. I assumed pink in line 8, and I just got the blue. That means that I'm done with that innermost proof. And that is because of line 12 by CP, conditional proof, which means now I can box and cancel that. So I can draw my box there and cancel the proof. Okay? And now that the proof is canceled out on line 7, I can use line 7. I'm not ready to use it yet, though, because I need to do another claim. I need to try to prove it the other way. Okay? I'm going to put this claim down here by the claim rule, and look why. See? Back at line 6, I'm trying to prove on the inside of those parentheses. That's a universal proof I'm doing in line 6. I'm trying to get what's inside those parentheses by itself, and that's a biconditional. I just proved in line 7 I got the forward of that conditional. Now in line 14 I'm going to prove the backward of that conditional. See that? All right, so what kind of a proof is this? This is a conditional. I'm trying to prove pink implies blue, and so I can assume the pink, and that's by ACP, right? Okay, now what? Well, we're going to use our rule substitution of equals. What substitution of equals says, if I have some pink statement with some red variable in it, and I have another statement which is an equation that says that the blue variable equals a red variable, then I could copy down the pink statement, putting the blue variable in for the red variable, right? As long as the pink and the blue variables are both free. Well, that's what I have here. Look, in line 4, I have FA, and the A is free, and that's my red variable. That's like the pink one here in the rule. Down here in line 15, this yellow one is an equation, like here in the rule, that says a blue variable, Z, is equal to a red variable, A. See, A is red up there. That means that I can put the Z in for the A, just like in the rule here, to get this, see? I know that FA means, whatever F means, AFs, whatever F means, means A is a frog, or A is an opera by Beethoven, okay, then, and Z is equal to A, that means that ZFs, Z is a frog, or whatever, okay? And so where does that come from? That comes from lines 4 and 15 by substitution of equals. All right, now what? Well, look. We got this line 14, we're trying to prove I think this is the shortest one we've done, and this little proof here is very short. We were trying to prove a conditional. Pink implies blue. We assumed the pink, and then the very next line we got the blue. That was quick. All right? And so that means that we're done with this, this little proof here that starts on line 14, because we reached the goal, which was the blue part of line 14. We reached that in line 16. We got the FZ. And so that means we can box and cancel. And that's by conditional proof, right? We box and cancel that. All right. So now both line 7 and line 14 have their proofs canceled out, which means they're available. And I'm going to use them now. Because look, this one here in line 7 says pink implies blue. And line 14 says blue implies pink. It's exactly, the blue is Z equals A, and the pink is FZ. So it's both directions, which means I can use my rule CB. If I know pink implies blue, and I know blue implies pink, then I can say pink if and only if blue, right? So that's what I'm going to say in line 18. I'm going to say FZ, I'm putting the pink one first. So the F, now I've changed it, now it's a biconditional in line 18. So I've got and that's coming from lines 7 and 14 by CB. Now I've written it as a biconditional, all right? Okay, now look. What we were doing in line 6, we were doing a universal proof, and we're trying to get what's inside the parentheses here, this pink statement with the blue variables. We're trying to get that free. And look what we just did. What we have here in line 18 is exactly what we need in line 6. That's the pink part inside those parentheses without the for all Z in front. And that means we have proven for an arbitrary Z that this thing is true. This is true for an arbitrary Z, which means it's true for everything. And so that is why we're done with this universal proof from line 18, where we reached the goal, which was to get the pink thing inside the parentheses. So now we can box and cancel. My rule's in the way. Let me get it out of the way so I can draw my box here. All right, so there's the box, and now we cancel the proof here in line 6. So now line 6 is available. Okay, so let's move on. Now what we're going to do next is we're going to use this rule existential generalization, which says that if I know something, a statement with a red variable in it is true, where the red variable is free, then I know that that same statement is true for something. In other words, there exists something for which it's true. So I can say there exists a blue variable for which that's true, where I put the blue variable in for the red variable, okay? And so what I'm going to pick, I get to pick any variable I want for that bound variable. I'm going to pick y, and I'm going to pick it because of something going on up here in my goal, what I'm trying to prove. If you see it says exists a y up there. I get to pick that, and I'm going to pick y. And so actually, I need to back up here. I'm going to use this on line 6. Line 6 is the pink statement with the red variable, which is A, okay? And now I'm going to write the yellow statement like this one here, where I've added on there exists a y, that's the bound variable I'm using, and I've copied the pink, but I've changed the A into a y, okay? And so that is from line 6 by EG, okay? And now, look, this is exactly what we're trying to prove in the main proof. And so we're trying to prove pink implies blue. We just got the blue. And so we're done by CP. And so we can box and cancel the proof, and there it is. And so now we'll move on to logic rule 15, which is very easy because we already did it. This is reflexivity of equals. We did this in video 2 when we were doing geometry proofs. It simply says anything equals itself. 25 equals itself. X equals X. This is reflexivity of equals, and here it is. This is exactly how we did it in video 2 with geometry proofs, and it says a red thing equals a red thing. Red variable equals a red variable, we can say. By reflexivity of equals, there are no arrows coming in, which means we don't need to put anything in the from column. We can just get it right out of the blue. Anything we want equal to itself. All right, and now we're going to do the next proof, and let's look what we're doing here. We're in the process of proving the LUF is equivalent to the muff. Okay, here are the form. This is the long uniqueness formula, the LUF, LUF, and here's the medium one. We're trying to prove that they're equivalent. We're trying to prove this one if and only if this one, right? LUF if and only if muff. And here is what we're trying to prove, the long hairy formula with the biconditional in it right there, see? So the long uniqueness formula if and only if, the short uniqueness formula. Now what we just proved in example 6, we just finished this, we proved that the LUF, if the LUF, then the muff. The LUF implies the muff. We just did that. And now in example 7, we're going to do it the other way. We're going to prove that the muff implies the LUF. Okay? So this the other way around. So here we go. So here we're trying to prove the medium uniqueness formula equals the long one. So here it is. I've turned it around the other way now. And there's a conditional sign right there. So on the left we have the medium uniqueness formula, and on the right of that conditional we have the long uniqueness formula. Alright, so we're going to use 4 columns obviously, and we're going to start with the claim rule. Once again, obviously it's not going to fit. We're going to have to use it up here and understand that that's what line 1 is, what's sitting up there, because it won't fit. That's by the claim rule. Okay, so now what this is, once again, this is a conditional, but we're doing it the other way now. We've got pink implies blue. We're trying to prove pink implies blue. And so we're going to assume the pink. And look carefully, make sure I copied that pink one down correctly. And we're going to try to get that long blue one. All right. And this is by ACP. Okay, now what? Well, let's look at this, this yellow statement here in line 2. This is an existential statement. The outermost part says there exists a y. Okay? And so we can use existential instantiation. Some y does this, which means I can pick a particular thing, but it has to be a brand new variable. Now, I used a in the other one, and if we wanted to put this together in one big long proof, the rule would be we couldn't use a again. I'm not going to use a. I'm going to use b, just to be clean about it. Okay? So what I'm going to do, here we've got exists a y, that's the blue variable like this, and then I got this pink thing in here with the y sitting there. Okay? And that means that there's some y that does this pink thing. So that means I can pick, I'm going to put b in. I say b does it. So like this. So I'm going to copy the pink statement, stripped off the exists a y, and now I've changed the y to a b, which is a brand new variable. And that comes from 2 by EI. All right? Now what? Well, let's look at this statement. This now is a universal statement. It says, for all z. Well, then that means I can use UI, and which means I can put anything I want in for z. So here we have for all z, and then a pink statement in the parentheses, where now the blue variable is z, and there are 2 z's inside the parentheses there. So I can pick anything I want to put in for z, because this is universal. So I'm going to pick b. I realize I already have a b sitting there, but I'm going to pick b anyway, because I can put anything I want in with ui. So here I'm going to copy the pink part down. Now what I did was I put a b in for each of the 2 z's. The other b on the right-hand side there, that just came along for the ride. And where does that come from? That comes from 3 by ui. All right? Now what? This here is a biconditional. We got pink, if and only if blue. And so what I can do is I can use my rule BC the second way to create the conditional. I can pick the conditional forward or reverse. I'm going to take the reverse one. So I got pink if and only if blue. I'm going to take blue implies pink. And that comes from line 4 by BC. Okay? Takes apart a BC takes apart a biconditional, right? Into one or the other of the 2 conditionals. All right, now what? I'm going to use this rule here. This is a new rule and also old rule. Reflexivity of equals. It says red thing equals a red thing. And I'm just going to do it. And I'm going to use B. I'm going to say that B is equal to B. Right there. Just like that. Where did that come from? That came from reflexivity of equals. I don't have to put anything in the from column. It comes out of nowhere. Anything is equal to itself. There's no arrow in that rule. Okay, now what? Look at this. I've got here in line 5, I've got if B equals B, then FB, and here I've got B equals B. So I've got pink implies blue, and I got pink, therefore I can say the blue by, from lines 5 and 6, by modus ponens. Now I have FB. All right, now what I'm going to do next, I'm going to turn around and go the other way, but with changing some variables around. I'm going to use EG now, which is the backwards version of EI. If I know a pink statement here with a red variable in it, so this is true for the red variable, that means it's true for something. So I can put an existential quantifier in front of it with a new bound variable, which is blue. So here I have FB with B as the red variable. That means I can, so BF, so B is a frog, that means something is a frog, okay? So I can say now, and I get to pick whatever variable I want for the bound variable, I'm going to pick T. And so I'm going to say there exists a T such that FT, okay? You see that? So I have, that's from existential generalization on line 7. BFs, therefore something Fs, and I can use whatever variable I want as the bound variable. All right, and that comes from line 7 by EG. All right, now what? Well, look, what I just got was a first part. Look, if I look at what I'm trying to prove up here on the right side of that conditional, that big hairy thing, that long uniqueness formula has two parts. It's got a conjunction, it's got an and sign right there. I just proved the left part. I got part of what I need. Now I need to prove the other piece of it. And what I'm going to do is I'm going to use the claim rule, and I'm going to try to prove that other part. So this is by the claim rule, and see, look at this. This is the other side. And when I have this, then I can put the two together with adjunction and get the whole thing, see? All right, so now, I'm trying to prove this. Well, this starts with for all W. This is a universal statement. So I need to use universal proof to prove this. And I need to do it on W. All right, so here, I'm trying to prove for all W this big hairy pink statement inside, which has, the W is the blue variable. And so it's got a couple of W's in there. All right, so now I need to prove that. But wait, before I can do this, I have to make sure that W is not free up there anywhere, because I have to make sure that W is arbitrary. Do I have any W's up here? I do. I have some W's right up here, which this is line 1, right? Okay, but now is this free or bound up here? Well, it's actually bound. This first one here, it says for all W out there is capturing that W, and that for all W is also capturing the other W. They're both bound, so it's okay, as long as it's not free anywhere. Are there any other W's up here? I don't see any. That means we're good to go on a universal proof. We got W is going to be arbitrary now, so we have to try to prove the part inside here without that for all W on the outside. We have to try to prove this pink statement with a free W. All right. Well, in order to do that, I'm going to make another claim. I'm going to try to prove this by the claim rule, and look what this is. This is just the very thing I just said we have to try to prove. Okay? So, now what? Well, once again, this starts with for all x. We have to do another universal proof. We have to use a universal proof inside of a universal proof here. The W one on the outside, the X one on the inside. All right, so here we go. Now the variable that we're proving on is x. So we're trying to prove for all x with this pink statement inside, which has a couple of x's. Once again, we have to ask, does x appear anywhere up here free? Well, do we have any x's up there? Yeah, we got some x's right up here in line 1. This is line 1. Now, is it bound or free? Are they? Well, they're bound. Look, this for all x here binds that x, and it also binds that x over there. Are there any other x's in here? I don't see any, so that means we're good to go. Nope, there are. There are some x's in line 9. Better check those. Are those bound or free? Well, look, this first x here, it's bound by the for all x there, and the other one is also bound by that for all x. Now I think I've got all the x's. And so they're all bound up there. None of them are free. That means for this proof here, x will be arbitrary. And so we're going to try to prove for an arbitrary free x without that for all x. We're trying to prove this pink part here for the free x, the free variable x. Okay. All right, now how am I going to do that? Well, I'm going to make yet another claim. Okay, now right now I've got my outermost proof on line 1 and the next level proof on line 9 and the next one on line 10. And I'm going to do another. I'm going to end again. Now I'm at 4 levels in. Because I'm going to try to, but this is by the claim rule, I'm going to try to prove exactly what I'm trying to get inside the brackets there in line 10. Okay? All right, so what is this? Now this thing is easier to handle. This is just a conditional. It says pink implies blue. And so to prove that, I need to assume the pink. And that's by ACP, right? All right, now we're getting into a little bit easier place here to operate. So, all right, now what are we going to do? Well, this thing here is a conjunction. It says pink and blue. So that means I can get the pink. I'll take the pink by using simplification. I can take the pink from line 12 by simplification, right? And now what? Look up here in line 3. Line 3, I have a universal statement for all z, and so I'm going to use UI, and I have for all z, and then this pink statement inside here with z as the blue variable. There's a couple of z's in there. That means I can write the pink one down, and I can put anything I want in for z. And what I'm going to put in for z is w. So I have copied the pink part of line 3 down here, and I've changed the 2 z's that are in the pink part of this up here. I've changed them both to w's, and I've copied all the rest. And so this is from line 3 by UI. All right. Now look at this. This is a biconditional, and I've got pink if and only if blue, which means I can use BC to pick off a conditional, and I'm going to do just that. I'm going to take it the forward direction, and I'm going to change this. I've got pink if and only if blue in line 14, so I'm going to say if pink, then blue. Pink implies blue, and where did that come from? Line 14 by BC, okay? Now what? Well, look at this. Line 13, I have pink here in line 13. I have pink implies blue here. Okay, these are both FWs. That means I can get the blue, and that is from lines 13 and 15 by modus ponens. So now I have W is equal to B. W equals B. What am I going to do with that? Well, hang on. Now watch what's going to happen next. I'm going to come back to this conjunction here that says pink and blue, and I'm going to use simplification again the other way. I'm going to get the blue one now. I'm going to pull off that FX, that blue part. So that comes from line 12 by simplification. Now I'm going to go through the same process all over again from this using X instead of W. All right, so I can use UI on line 3 up here on the Z. So I've got a Z here, and I can put anything I want in for the Z in that pink, and this time I'm going to put X in. And so that's what's going to happen here. So I've copied the pink part here, now putting X in, because it's UI, if it's a universe, I can put anything I want in. All right, and so this is from line 3 by UI. See that? All right. And now once again, this is a biconditional, so I'm going to use, it says pink if and only if blue. I'm going to use BC, and I'm going to do in the forward direction, and I'm going to get the conditional. I'm going to say pink implies blue in line 19, copying this down, changing the biconditional to a conditional. So that's from line 18 by BC. And now, once again, just like before, look, I have pink here, and I have pink implies blue here. And so I can use modus ponens and get the blue. And so that's from lines 17 and 19 by modus ponens. And so I did the same little process in lines 13 to 16. I did this process on W. And then I did the exact same process on line 17 to 20 on X. All right. Now, we're going to use a rule substitution of equals, and this time we're going to use it in the simplified way that we did back in the geometry videos. What we have here is we have that W is equal to B, and also that X is equal to B, so that means that W is equal to X. Let me show you how it works in the general rule here. You see, if we they're both, the simplified cases in both of the statements are equations. Here we'll let the pink one be this one here, W equals B, with B as the red variable. And this one here, this one says that X is equal to B. That means that we can put that blue variable in, X, where the B is. So we can put the X into the pink statement and get this. W equals X. Okay? So that's from 16 and 20 by substitution of equals. All right, now what? Well, look what we were doing. We were trying in line 11 in our innermost proof, we were trying to prove pink implies blue here. We assumed the pink. We just got the blue, W equals X. And so that means that we're done with that proof by, that comes from line 21 where we reached the goal, the blue goal, by conditional proof. So we get to box and cancel that proof. Okay, and now look. Back in line 10, we were doing a universal proof. Line 10 is a universal proof on X. All right, and so what we were doing is we were trying to prove that pink part inside there. Show it for all. We're trying to prove this. We need to get the part that's pink in there with the blue variable free. And look what we did. That's exactly what we got in line 11. The proof is now canceled out on the line 11, so this is available. And here it is. It's exactly the same as the pink part in line 10. So for an arbitrary X, that means it's true for all X. So we're done with this from line 11 where we got it by universal proof. So now getting that rule out of the way, I'm going to box and cancel like that. Okay? And now what? Now going backwards again to line 9, remember we did two universal proofs, one inside the other. This one on the outside is on W. So we were trying to prove for all W this pink thing here, which includes the for all X part. And we needed to prove that for a free blue variable W. Well, we just did that. That's what we have in line 10. Exactly that, without the for all W on the outside, which means that we're done with the proof in line 9. And that comes from line 10 where we reached the goal of that pink thing with a free blue variable by universal proof. And so getting the rule out of the way, I'm going to box this and cancel this. Okay? And now what? Well, look at what we have here. We have a pink and a blue. And so I can use the rule adjunction to put the pink and the blue together to get pink and blue, which I'll do right down here. Okay, pink, that's the exicitive FT, and the blue is this big long thing here, which I've copied, and so this comes from 8 and 9 by adjunction. And now look, this is exactly what we were trying to prove. This is the long uniqueness formula, right here in line 25. And so we were trying to prove that the short uniqueness formula implies the long uniqueness formula. We assumed the short uniqueness formula. We just got the long one. And so that means we're done with this one by conditional proof. It comes from line 25 where we reach the goal, which means we by CP. So we can box and cancel. And so we're done with that proof. Okay? And so what we're doing is we're proving that the long uniqueness formula and the medium uniqueness formula are equivalent. We want to prove this, that the LUF if and only if the MUF. In example 6, we proved that the LUF implies the MUF. In example 7, we just finished proving the opposite, that the MUF implies the LUF. And so now we can use CB to combine the forward and reverse conditionals to get the biconditional. LUF if and only if MUF, which is this enormous thing here. All right, in other words, the long and the medium uniqueness formulas are equivalent. All right, now let's talk about the short uniqueness formula. And the medium and the short, getting to and from the medium and the short with rules. Okay, here we are in the outline. So we're going to go from the MUF to and from the SUF by a pair of rules which are called MUMPUS and SUFFUM. So here's the medium formula, here's the short uniqueness formula, which simply says there exists exactly one thing that F's, using the exclamation point. And this is an abbreviation for this. We need the medium one in proofs. And then this one, we'll use it in proofs too, but we'll always get it directly from this. And so, because it's just an abbreviation for this. But this is sharp and easy to see what it says. That's why it's valuable. So all three of them are important. Now to get back and forth between the short and medium formulas, we need these two new rules. The first rule is medium uniqueness formula to short. In other words, MUFS, MUMPUS. This goes from the medium formula to the short formula. And the other one is the short uniqueness formula to the medium, SUFM, SUFM. It goes from the short formula to the medium formula. Now we don't actually need this last one in the proof, in the G proof, but I'm putting it in for completeness. Because remember that the short formula is just an abbreviation for the medium formula. Okay, so here is Memphis, the medium to uniqueness formula, short. So look at where we're going. We have a statement of this form. We can get a statement of this form. And what does this say? It says there exists a blue variable such that for all of a red variable, then in big parentheses, a pink statement with the red variable in it, if and only if the red variable equals the blue variable. And that is the medium uniqueness formula. If we have that, then we can say this. We can say the short one. In other words, exactly one purple variable such that whatever the pink thing is with the purple variable in there. Okay? So that's going one way, and then SUFM just goes the other way. Just turn that upside down, but we're not going to need that. Okay? And now let's look at all three formulas, the long, medium, short. And to get from the long to the medium, we proved that the long implies the medium in example 6. We did it the other way in example 7, so these two are logically equivalent. This introduces a new quantifier, the backwards E with the exclamation point, and we're declaring that as an abbreviation for the medium. And these two rules, Memphis and SUFM, go back and forth by that definition. Okay. So now we'll move on to descriptions. Logical the. Here we are in our outline. We're at the last entry. We're almost done. Now the description operator, this candy cane is called the description operator. It means the. And we talked about uniqueness and the in video 1. So now we're coming back to that. Now what does it describe? What do we call a description? What it describes is something that is unique. So now supposing we know the short uniqueness formula is true for a predicate J. So I have this right here. This says there exists exactly one X, or there exists a unique X such that JX. That says exactly one thing J's. Maybe J means blank jumps. Okay, exactly one thing jumps. That's what it says. It's not going to be true, but anyway, that's what it says. All right. Now this means, now look what we do. We treat the syntax of the candy cane is somewhat like the quantifiers, but there's a difference. I'll explain that in a minute. We say with the candy cane, okay, so there, the X, we read it, the candy cane X, so the X, and then in parentheses it says JX. What this means is, it means the X such that JX. In other words, the unique thing that J's, whatever that might be. Okay? And I'm going to explain with some examples exactly what that is in just a moment. But just talking about the grammar here, the syntax for a moment. The candy cane is like the quantifiers in that it binds a variable. See the X there? When we say the X such that JX, X is bound. It's a bound variable. It's not free. But it's unlike the quantifiers in that it produces a term instead of a sentence. When I say for all X stuff, I get a sentence. But when I say the X stuff, that's not a sentence. I get a thing. I get a term, not a sentence. Now, let's look at an example of how we use the description operator properly. So let's let J mean this predicate right here. Blank is a nation bordering Portugal. We'll have a map here of the Iberian Peninsula in Europe, and you can see here's Portugal on the left by the Atlantic Ocean, and there's Spain, and up in the north there's France, and you can see the tip of Morocco down there. Now what does this sentence here say? This says there's exactly one thing that J's. There's a unique X that J's. In other words, now using our predicate with J, what this sentence says is there exists a unique X such that X is a nation bordering Portugal. In other words, it says exactly one nation borders Portugal. This is true. Look at the map. Portugal has the Atlantic Ocean on one side and Spain on the other side, and there's no other country. It borders Spain, and that's the only thing it borders. It doesn't border any other country. So it's true that it borders exactly one nation, and that nation is Spain. Now, what the description operator does is it grabs that unique thing. Okay? What is the unique thing that borders Portugal? The only nation that borders Portugal is Spain. So the candy cane grabs Spain. And so what we get is, in other words, we get the X such a JX means the X such an X is a nation bordering Portugal. The X such an X is a nation of which there's only one. So the nation bordering Portugal. This means the candy cane, the X such a JX means the thing that uniquely borders Portugal, and that is Spain. So the description operator is grabbing Spain. In other words, the X such a JX equals Spain. You see that? So it gets the Spain, and there's only one, and so it makes sense. It's well defined. If I say the X such a JX, it makes sense. And because it makes sense, it's called a proper description. And why does it make sense? Why is it proper? Because we prove uniqueness. Because the uniqueness works. If the short uniqueness formula is true, it's true that there's exactly one nation that borders Portugal. Because that's true, because the uniqueness formula is true, the description operator makes sense. We get a proper description. Now, let's look at the other way. There's actually two other ways in which it can be improperly used. Supposing J means blank is a nation bordering Australia. Well, here's a map of Australia. Well, you know what? Australia is completely surrounded by ocean. It doesn't touch any other nations. So if I say if I say there exists a unique X at JX, in other words, there exists a unique thing X, such that X is a nation bordering Australia. That's false. No nation borders Australia. There is no unique nation that borders Australia. So, the nation bordering Australia, that phrase, makes no sense. There is no such thing. And because uniqueness does not hold, if I write the X such that JX, when this is the predicate J, that is garbage. And so it is called an improper description. When the uniqueness formula is false, then the description operator produces garbage. That's the first way. There's another way it can produce garbage. Let's look at this one, the second way. Supposing J means blank is a nation bordering Brazil. Well, here's a map of South America. And the thing about Brazil is it has a whole bunch of countries that it borders. And here we have the X, the unique X, such as JX. This says there exists a unique thing X, such that X is a nation bordering Brazil. There exists a unique thing, a unique nation bordering Brazil? Nonsense, that's false. Many nations border Brazil. So if I say the nation bordering Brazil, it makes no sense. And why? It makes no sense because the uniqueness doesn't hold. That means that the X, such a JX, is garbage. It's also an improper description. So to get a proper description, the short uniqueness formula has to be true. Otherwise, the description operator produces garbage. Okay, so that's it. We have finished our crash course in predicate logic. And so now we're going to use this. When we get to video 8 to do our formal rigorous proof. All this stuff I've taught you about logic, all these rules, all these ways, all the stuff that goes on in the proof, we're going to do all that stuff when we do our rigorous mathematical proof that God exists. We're also going to use in video 9, when we make our formal definition of God, look at that. It has the candy cane. It says God equals the G such that SG and OG. So we have to prove uniqueness first, but that's what we do in the G theorem. So we're going to use these ideas about when we get down there. Okay, and so that's it for video 5. We're done with video 5. The next video is video 6, where we're going to start our process of actually proving that God exists with the undefined terms, definitions, and our first 3 axioms. I hope to see you there, and thank you very much for watching. I'm Mark Lawrence Donald Emerson.